Let's get started. Welcome everyone to the Simons Institute. Of course, many of you are here long term, but I know there are also people coming here just for this week. So my name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute, and it's my pleasure to invite you all to this workshop. A brief blurb about the Simons Institute. For those who may not be yet familiar, which is probably a likely crowd in the theory community, but we are the leading venue for collaborative research in theoretical computer science and related areas, this was established in 2012 with a generous grant by the Simons Foundation, and every semester it brings together a lot of researchers in specific areas, widely varying areas of theoretical computer science. And this is the 10th year of programs at Simons, and we're really proud of the achievements of the programs which have pushed the frontiers of TCS in so many directions. They've resolved long-standing open questions and have also opened up new lines of inquiry. And each semester program attracts around 70 long-term visitors, junior and senior, to Berkeley, and also includes a boot camp and 3 workshops that convene more short-term visitors. And I would like to welcome you to the workshop on lower bounds learning and average case complexity, which is the first of 3 workshops in this semester's program, which focuses on meta complexity. And I would like to thank the organizers of this workshop for their work in putting together a great program. And they are Valentin Cabinets, who's sitting here, and I'll hand it over to him shortly, and Igor Oliveira, who's here, and Russell Impigliazzo, who did the work, but then he will be here. And thanks everyone, so the organizers. There's Russell, okay. So, let's give them a round of applause. And a few logistics for the coming week. The food is provided before the first talk and during the breaks, just outside where you are now. For lunch, you are on your own, but there are many excellent options in walking distance. And the weather, I think, will be good this week. And we do ask that you please leave any food and drinks outside the auditorium. Water in bottles is okay, but no beverages or food. So that keeps the auditorium clean. And if you do need to store something while you're going for lunch, like your backpack or coats, there are lockers on the other side. Please use them. And for all talks, Omiyad Far is here, our videographer, and he will help you set up, and any questions you can ask him. And I'm not sure if this workshop is hybrid. Okay, if it is hybrid, so if you're here in the room, of course, ask questions by just raising your hand. And if you're attending remotely, I believe someone will be monitoring, and you can ask questions on the chat. Okay. And finally, I would like to give a thanks to the organizing, the events team, without whom the event would definitely not happen. Kelani Penland, Ashley Hassan, and Elizabeth Ewan, and they manage all the logistics for the week, including the accommodations for out-of-town visitors. So I think let's give them an applause as well. And, with that, I'll hand it over to Valentin to introduce the workshop.
Thank you very much, Venkat. Thank you for coming, and on behalf of Russell, Igor, and myself, welcome to the workshop. It's the first workshop in a series of 3 workshops, roughly on complexity, logic, and cryptography. And so this is a complexity one, and roughly connected to the theme of meta complexity. We have lots of talks. The first day today is special day to honor Eric Allender, who was doing time-bound Kolmogorov complexity before it was cool. So now we have a special semester. Thanks to people like him, we have the special semester at Simons that talk about time-bound Kolmogorov complexity and meta complexity. Eric has lots of contributions to meta complexity and theoretical computer science, some of whom will give talks later today. But we'll start with Rahul Santhanam, who'll talk about some of the work that Eric Allender has done for meta complexity. So please.
Hi, so can you hear me? Yeah. It's really a privilege to be here today and to talk about Eric's work. I mean, as Valentin said, without Eric's work, we couldn't really imagine this program happening. So perhaps the most influential body of work for this program. So right from the beginning, when we wrote the proposal, we had earmarked a day to celebrate Eric's work, and organizers chose this day. And so tomorrow is Valentine's Day, but today is Eric's Day. For those of you who haven't been in the semester so far, just a very kind of a quick slide about meta complexity and what it is, just that we're all on the same page. So metacomplexity studies the complexity of problems that are themselves about complexity. And prime examples are the minimum circuit size problem and the problem of time-bound Kolmogorov complexity. And well, I mean, this sort of, these questions have applications to a variety of other fields. They have applications to complexity low bounds, of course, since they're about complexity low bounds, but also to learning, to average case complexity, cryptography, and proof complexity. And we'll be hearing about all of these connections through the semester. We already heard about them during the boot camp. But for this talk, I'd like to kind of like take a more historical perspective, which actually Eric already did to some extent in his CARP lecture a couple of weeks ago. So computer science is a very sort of a field that's quite obsessed with being in the present and the trends and so on. And metacomplexity is the opposite of that, because it's something that's been, that concerns foundational questions that have been around for a very long time without us making much progress. And even if we live in the present, we need the past to understand and explain the present. So metacomplexity might have a lot to say for the future of foundational questions, but the question is, what did we do for metacomplexity and what did metacomplexity do for us? So here's sort of a little bit about the history of metacomplexity. So the prehistory of metacomplexity. So there are several papers that sort of talked about the complexity of complexity sort of implicitly or in sort of scattered ways without there really being a coherent theory of this field. So I'd just like to say a little bit about some of these papers. So starting off with the work of Kolmogorov and Levin. So right from the beginning, I mean, Levin's work has been very concerned with Kolmogorov complexity and using that as a tool to understand computation and information. Right from his paper where he proves the NP completeness of various problems, including satisfiability. One of the other problems that he proves NP completeness of is a version of the minimum circuit size problem for DNFs. So that's nearly 50 years ago. And then he defined his notion of time-bound Kolmogorov complexity and studied its properties. Then there's also actually a Berkeley connection to metacomplexity. So the first conference paper that the Vazirani brothers ever wrote was on metacomplexity. So it's really a question about a problem about time-bound Kolmogorov complexity, a sort of restricted version of it. They showed that this version was NP complete under randomized reductions. And their motivation was quite different. They weren't so much concerned with the problem being important, but they were concerned with the power of randomized reductions. And they were interested in finding a natural problem that would be NP complete under randomized reductions, but wasn't known to be NP complete under deterministic reductions. So that was their motivation. And I think it's not a very well-known paper, so I thought I'd kind of highlight that. There's all this work in the Soviet Union, the 50s and 60s on metacomplexity, which wasn't really, I think, well known in the West until maybe Trachtenbrot's survey, where he talked about this work in the 50s and 60s, even predating Kolmogorov and Levin. There's the famous paper of Impagliazzo and Levin about average case complexity, and that has a section on metacomplexity in a way. There's Koh's paper, which is about the hardness of proving NP hardness of metacomplexity, and he gives like an oracle letter to which is not true. So there's other papers perhaps not as well known as it should be. So there's various works sort of like scattered around, but not really, I think, like connecting with each other or sort of like trying to establish or kind of broader theory. And then there's these works in the 90s and in 2000. So the Rasparov-Rurich paper on natural proofs was extremely influential because even though it didn't explicitly use the language of metacomplexity, it was really talking about that. And it sort of foreshadowed future links with a variety of areas, with the cryptography, with learning, and proof complexity. And then in 2000, Valentin and Ginny Tsai defined and studied the circuit minimization problem, MCSP. So they're the first ones to define MCSP, and they kind of had various interesting results about its relevance to complexity theory, especially. So why is it hard to prove NP hardness, but also what kinds of consequences would it have if MCSP is in P? So various results of that form. And that's really what I think set things in motion in terms of studying metacomplexity more in a more focused way. But it took a while. And while it did, I mean, Eric was publishing a lot of papers on metacomplexity. Yeah, so let's kind of like look at some of these. Yeah, so there's this kind of paper, which is a survey in FSTTCS in 2001. And that's, so as you'll see, there's a lot of papers that Eric wrote. And when I was preparing for this talk and thinking about what I'd say, there's a question of how to best sort of summarize or discuss his contributions. Should I sort of like do like a highlights tour? I finally decided it would be best to focus on this one paper because that's, as far as I can tell, the earliest paper wrote on metacomplexity. And for me, at least, it's been very influential. I think, as you'll see, I'll kind of like explain how it connects to various lines of work in our area. So that's what I'm doing. But I did want to kind of show you a list of papers that he wrote. I mean, he was publishing constantly through the early 2000s, especially. There's this kind of power from random strings paper, on the paper that's been very influential. This paper in which they defined other notions of Kolmogorov complexity. Then there's this whole program that he had about which languages are efficiently reducible to the Kolmogorov random strings and various resource-bounded versions of it. So this was part of that paper. Here's a paper with Tony and Mike and others on the MCSP problem restricted to DNFs and constant depth circuits. Here's a survey that he did, yeah, another survey, several other papers. So as you'll see, he was constantly publishing through the early 2000s at a time when not many other people were. In fact, I have a sort of conjecture to make. It's a historical conjecture that I haven't been able to verify. But as far as I can tell, between like 2001 and 2012, 100% of papers on metacomplexity had Eric as an author on them. And even if this isn't quite true, it's approximately true, I think. So he was advocating for it and kind of like, and clearly working on it, but he wasn't yet able to convince other people to work on it with him or in their own right. And people did eventually listen, but it took a while. So yeah, what I'm going to be focusing on is this paper. So it's a fairly short paper. It's a survey, more or less, in FSTTCS, or it's disguised as a survey. As I'll argue, it has lots of interesting things to say, sort of new connections to make, new theorems which are disguised as observations, and kind of yeah, suggestions for further directions and so on. So it's actually quite a rich paper. And I'd like to kind of bring it to people's attention more and to talk about how it connects to current day work. So here's like the title and abstract of the paper. So yeah, this paper is the following goals: to survey some of the recent developments in the field of de-randomization, to introduce a new notion of time-bound Kolmogorov complexity, K capital T, and show it provides a useful tool for understanding advances in de-randomization, to illustrate the usefulness, and to pose some promising directions for future research. So yeah, very modest abstract. So, and that's, I mean, but it's a sort of grand title and kind of like, yeah, and indeed it connects sort of like very areas that don't seem really that closely connected, and sort of showcases the importance of Kolmogorov complexity in these areas. So in a way, this talk is going to be a commentary on the paper. So I'm going to kind of like discuss what the paper does and sort of how it connects to what's happened since. So there are these various things that the paper does, right? It sort of introduces and motivates a new concept, the concept of K capital T complexity. It finds these new characterizations of well-known complexity questions in terms of variants of Kolmogorov complexity. And then it proves this sort of new low bound, proves or observes a new low bound, and it points the way to several others. And it identifies various interesting open problems and directions. So there are concepts, there are new connections and characterizations, there are new results, new open problems, directions. And I want to kind of like talk about how all of this, how various lines of work nowadays can be traced back to themes in this paper. So let's start off with what K capital T complexity is. And in order to talk about that, let me say a bit about what metacomplexity problems we can define just based on standard notions of circuit size and Kolmogorov complexity. So if you haven't really seen metacomplexity very much, so here are some fundamental problems about complexity. Minimum circuit size problem: given the truth table of a Boolean function f and a parameter s, does f for Boolean circuits of size s. So that's, yeah, perhaps the main problem of the area. Then there are all these versions of Kolmogorov complexity. So there's plain Kolmogorov complexity, where you're asking, given a string and a parameter, does the string have complexity at most that? And here the Kolmogorov complexity is the minimum program size to produce that string from an empty input. You can also define conditional versions where this input here is a string y, and then you're asking for the smallest program to produce x from y. And then there's a time-bounded version where you have some a priori time bound, let's say n to the 100, and you want to know whether there's a program that produces x from in time n to the 100. N is the size of x. So t is a polynomially bounded function we fix in advance, and we want to know whether you can produce x efficiently. And this seems more relevant to complexity theory because there's a problem in NP. You can guess the program, and then you can check that it produces X within polynomial time. And then there's a k little t notion, which is defined by Levin. So given a string and a parameter S, is k little t at most S. And how is k little t defined? Well, it might not seem very intuitive at first. So essentially, you take the program size, and then you add like a further term to it. In this case, it's sort of a logarithmic term in t. And yeah, it's not clear why logarithmic is the right function. And as we'll see, Eric makes a different choice when he defines k capital T complexity. So the minimum over program size plus log of the time bound such that u of p comma epsilon outputs X within t steps, right? And the significance of this notion is it somehow captures the complexity of search for witnesses. It kind of can be used to argue for like an optimal algorithm for searching for witnesses of NP problems. But yeah, we won't get into the motivation here. This is just kind of an interesting notion of Kolmogorov complexity. So there's various notions here, and one of them isn't like the others, right? So three of those notions are really about Kolmogorov complexity, and MCSP isn't. It's defined in terms of circuit size. So it's clear that MCSP is a problem about compression. I mean, circuits are compressions of truth tables, compressed representations of truth tables. So one could ask, is there a natural sort of Kolmogorov-like complexity measure? So complexity measure based on some sort of like, on standard Kolmogorov complexity, some variant of it that can be used to characterize and understand MCSP.
That's an online question.
Oh, yes.
So Emmanuel Viola is asking, what is epsilon this time?
Oh, it's the empty string. Yeah.
Okay.
Yeah, so is there a natural Kolmogorov-like complexity measure that can be used to characterize and understand MCSP? Here's what we can notice. So if you're asking about MCSP, you want to know whether Y is a truth table of function. You want to know if it has small circuits. Well, a circuit C for F can be thought of as a program for Y that can be used to compute Y locally, right? So a circuit is a program such that given any bit of Y, you can kind of recover that bit from the program in time proportional or slightly more than the circuit size. You just run C on I, the binary representation of I, and that gives you the bit Yi. So it is kind of a program, but a program where kind of like the computation kind of happens in a local way for Y. So that sort of maybe gives us a hint about what to do. And Eric made this definition. So K capital T, and the capital T is because time plays a bigger role in this definition. It's sort of there's a larger factor depending on time than for K little t, and that's the reason for K capital T. So minimum of program size plus time such that u of p comma I outputs the ith bit, X sub I here is the ith bit within t steps, right? And you should really be thinking of t as sublinear here, right? Because X can be computed with a program of length size of X or slightly more with just sort of like to output the ith bit of X, you just look at the ith bit of the program, right? So that's like a trivial way to compute X. You really want to know what you can do with smaller time bounds, with sublinear time bounds, with small programs. So Eric proves that K capital T of Y for any string Y and the circuit size of F sub Y, which is just the function, the Boolean function corresponding to Y. You can assume that Y is a string of length, say 2 to the n, maybe truncating it to the largest power of 2 smaller than the length of Y. So you can just kind of make sure that Y is a length of has length the power of 2, and then that corresponds to a Boolean function whose truth table Y is, that's F sub Y. And the circuit size of this function F sub Y and K capital T of Y are polynomially related to each other, right? So it's sort of really capturing circuit complexity or a good approximation to circuit complexity. And that's not very hard to prove based on what I said before about local computation. If you have a circuit that computes Fy, then that can be the program. And the time taken by the program is sort of proportional to the circuit size. So you get some sort of approximation factor there. And the other direction, if there's a program that computes Y sort of implicitly in this way, locally, then just by using the simulation of time by circuits, you can get circuit out of it, right? So both directions aren't hard to show, but it's an important notion. And one could ask, is it a natural notion that relates to previously defined resource-bounded variants of Kolmogorov complexity? And it turns out, as was shown by, so I should have mentioned Detlef Ronneberger, who showed this, that if A is any language complete for linear exponential time under efficient reductions, under linear time reductions, then K capital T to the A, so you can define an oracle version where this universal machine has access to an oracle A. So if you have oracle an exponential time language, a complete language, then that is within a linear factor of k little t. So really, k little t is kind of fundamental, even though it is defined last. And in fact, if A is, say, a linear space complete language, then you get the space-bounded version of Kolmogorov complexity. So it does relate to the previously defined measures. But you might still ask, well, what's the point of k little t? Why should we care about k capital T rather than circuit size? And one major reason is we don't understand the circuit size of a random Boolean function on n bits as well as we would like. So a very long time ago, Lupinov showed that circuit size is this quantity, but it's not as good. I mean, it's pretty good, but it doesn't like capture the expected circuit size of a random function to within, say, a good additive term. So we don't know what it is precisely. And the variance isn't as small as we'd like. And it's far less precise in understanding of Kolmogorov complexity and its variance. Because for all the versions of Kolmogorov complexity we have, each string of x of length n has complexity at most n plus log n plus order 1. In fact, for most variants, it's n plus order 1. For k capital T, it's n plus log n plus order 1. So each string has a small description in terms of its length, and most strings have large descriptions, right? So if you look at the probability that a string has complexity at most n minus k, it's like a geometric distribution. All but 1 or 2 to the k fraction of strings of length n have complexity at least n minus k, and that's by simple counting argument. So most strings have complexity very close to the maximum. And in fact, this has been key in some more recent work connecting Kolmogorov complexity to cryptography. So this is very nice, and we'd like to have something as close to this property as possible for circuit size, but we don't know how to. So this more precise understanding of compressibility for Kolmogorov complexity and its variance allows us to prove tighter and more results for the meta-complexity version of k capital T, right? So circuit size has this meta-complexity problem MCSP. Similarly, we can define a meta-complexity version of k capital T, and this sort of like more kind of precise understanding of k capital T allows us to prove better results, and we'll see how now. So what's mk capital TP? Given a string x and a parameter s, you ask, is k capital T of x at most s, right? So is the k capital T complexity at most s? And here, just like a couple of results which show why mk capital TP is like a good notion to try to approach results about MCSP, right? So if you have a result about MCSP that you want to establish, it seems that a good strategy is to try to prove it for mk capital TP first, because it's more tractable or it's easier to analyze. So it was shown in a paper of Eric and Shuichi, and then a paper of Shuichi and me, that that mk capital TP is not an AC0 mod P for any prime P, so a low bound against AC0 mod P. But showing the same low bound for MCSP was turned out to be a much harder question. And then Valentin, Russell, Antonina, Rahul Lulango, and others kind of showed that this was indeed the case, that MCSP was not an AC0 mod P, and the proof there was more complicated. So it did require a bit more work than this proof. So this kind of like gives us a sense that maybe this result holds and maybe points the way towards some ideas, but then more work is required to complete the proof for MCSP. So this is a case where a result for MCSP was shown by first showing a similar result for MK capital TP, and then kind of, maybe building on or kind of bringing in some new ideas. And there's several other cases where we know the result for MK capital TP, but we don't know it for MCSP, and whether doing it for MCSP is still open. So, I mean, I guess these are all kind of like open questions in a way for this program. So cases where they're kind of like, kind of important results that we want to show. So one result, for example, that showing evidence for the hardness of these problems, right? So we know that these problems, just from Rasparov-Rubich, we know that these problems are hard if one-way functions exist. So under standard cryptographic assumptions, we know that they're hard. But can we show hardness under other assumptions, average case hardness assumptions? So it was shown that MK capital TP is hard under, say, the planted-clique hypothesis, and under Feiber's hypothesis on average case hardness of KSAT. So these are sort of average case hardness assumptions, that are not sort of like implied by the existence of one-way functions. And we don't know this for MCSP. So we know that MK capital TP is hard. We don't know that MCSP is hard. I mean, it seems absurd that MK capital TP could be hard, but MCSP not, right? They're so closely related. But as far as we know, we can't rule out the possibility that MK capital TP is NP hard and MCSP is NP, as far as I know. So we still don't kind of understand the relationship between these problems very well, but we do expect that similar results hold for them. So that's one example of something we don't know for MCSP and would like to know. The result of Handel and Wren showed that MK capital TP is hard on average with a uniform distribution. So you kind of choose a string from the uniform distribution and you want to know, you ask the algorithm to compute its K capital T complexity or to decide its K capital T complexity. And for a certain notion of hardness, mild average case hardness, it turns out this is the case if and only if there's a one-way function computable in NC1. So it's really a characterization of parallel cryptography, the average case hardness of this problem, which I think again motivates this notion and shows that it's important. On the other hand, we don't yet have a good characterization of the average case hardness of MCSP or the uniform distribution. That's like a long-standing open problem to try to do that. There are some partial results, but it's still not clear exactly what the characterization is. And the barrier is precisely what I said before, but the fact that we don't understand the distribution of circuit size very well. Yeah.
Between MKTP and CSP, because if these define approximately the same thing, not like the circuit size, so why is it possible?
Oh, okay, yeah. I mean, it's a very good question. I mean, the reason is that they're approximately the same in terms of being a polynomial factor of each other. But many of the results that are shown for MK capital TP are about thresholds or complexities that are very close to n. So, for example, complexity like n minus root n. And there is no clear connection or implication for circuit size. I mean, if we showed results for, say, K capital T complexity, say, n to the 1/3, then it would imply something for circuit complexity. But we show something for, say, K capital T complexity n minus something small, that doesn't seem to have any direct implications for circuit size. Yeah. So there are like various situations in which we can compress strings a bit, but we don't know how to get small circuits for them. So if like a graph has like a large peak, we can compress it a little bit, but doesn't mean that the graph can implicitly be described by small circuits. So that's kind of like the intuition behind this first result here. And so it's just an example. Yeah.
Isn't there a thing where if you add multiplexers to the circuit, like everything's fine? Like,
I don't know if it's
kind of, that's a little wishy-washy. So yeah, that's
it's not clear it's fine in all cases. I'm not sure. Yeah.
So one way to fix this situation would be to show that MKTP, approximating MKTP is equivalent to computing it exactly.
Yeah.
Right?
Yes,
So then
yes.
we could
Yes.
get rid of all these fudge vectors and everything would port.
Yeah, that's exactly right. And I think like for all of these problems, like approximation, hardness of approximation is an interesting problem. But for MK capital TP, it has this nice consequence that will imply results for MCSP directly. Yeah.
so what kind of pattern would you need for what kind of an approximation?
I think you need like for if you're looking at strings of length n, well, it's a function of the parameter. So like maybe s squared or something, but maybe even a constant factor might be enough, but I'm not completely sure.
So it's known that like if MCSP is like NP hard under deterministic reductions, that like X is not equal to EPP, is that right?
Yes.
So like does a similar thing hold for MKTP?
Yeah, the same proof holds.
So showing it's NP hard is all right. Going NP hard.
Yes, but under a specific kind of reduction, which yeah, I mean, we could use randomness if we wanted or non-uniform.
Yeah, sure.
Under standard notions, under the notions we've typically used so far. Okay, and then there's this kind of like really nice recent result of Eric and Shuichi and a couple of students who show that MK capital TP does not have polynomial-sized threshold or majority circuits. So you have like depth 2 circuits where the top gate is a threshold gate, an arbitrary threshold gate, the bottom gates are majority gates. So this is like the sort of the frontier of low depth complexity low bounds, right? We don't know like low bounds against depth 2 threshold circuits. We don't know if NP has polynomial sized depth 2 threshold circuits, but we do know that yeah, even inner product doesn't have sub-exponential size threshold and majority circuits. And one of the kind of projects in meta complexity is try to transfer all of these explicit hardness results to the meta-complexity problems to show that they hold also for the meta-complexity problems. And one class that had sort of resisted this for a long time is this class of threshold majority. But yeah, this result cleverly sort of gets around that. And this is again something we don't know for MCSP. We know it for MK capital P, but we don't know it for MCSP. So essentially, I think any like known kind of low bound for an explicit function, circuit low bound, we also know for MK capital P, I think pretty much. If you know of any counterexamples, then let me know. But as far as I'm aware, we know all the low bounds that we know for explicit functions.
So this circuit classes is known to have low bound, explicit low bound?
Yes, yes. Inner product is hard for that. Yeah.
Oh, it's one gate of threshold and then majority. It's not more than two.
Yeah, I mean that's more than two is and even that's two if they both layers of thresholds is very hard. But yeah, if there's only one gate.
It's very sad. This was like known in again like in the late 80s. It has a very simple proof for the lower bound, and yet we haven't even budged.
Yes. Yeah. But we have to celebrate that.
You have like a moment of silence.
It was pretty extraordinary that you kind of, just converting a top gate from majority to threshold. I mean, it doesn't seem like it should give much computational power. And it's just that we don't know how to argue about it. Okay, so that's all I'm going to say about K capital P complexity for now. And now I'm going to talk about characterization. So something else that Eric does in his paper is to give new characterizations of well-known complexity questions in terms of variance of Kolmogorov complexity. Okay, so what's this about? So, well, various notions of resource-bound Kolmogorov complexity are useful in characterizing various important open questions in complexity theory. And the hope is that these characterizations, because they're in terms of a few basic notions of Kolmogorov complexity, will lead to new connections and approaches to these questions. And Eric's paper gives some examples of such characterizations. So I just want to show you a couple of examples and what they look like. So here's a characterization of the kind of the assumption of the statement that E is hard in non-uniform setting, right? That E requires exponential size circuits. So let's just make a definition. So we know what K little t is. So let's define K little t sub L of n. So that's just the smallest K little t complexity of any string in L, right? So let's assume for now that L is sort of non-empty at every input length. And if it isn't, we just ignore those lengths. And at the lengths where it's non-empty, we take the x with the smallest K little t complexity, and that's going to be this this function, K little t sub L of n. And then Eric shows like sort of a series of equivalences. He shows that E requiring large circuits, requiring circuits of exponential size, that was already known to be equivalent to the existence of pseudorandom generators through the work of Russell and Avi Vigdisson. What Eric shows is that this is equivalent with a couple of other statements that are phrased in terms of resource-bounded Kolmogorov complexity. So one of these statements is that for all dense languages in P/poly, so all dense languages, meaning languages that have at least 2/3 of all strings of length n, there is going to be some string with small K little t complexity, order log n K little t complexity. Essentially, the idea here is that if you have a pseudorandom generator, then the seed will describe kind of some output of some member of the range, which is in L, right? So that's the idea here. So that turns out to be equivalent to these two other items. And then there's this kind of statement where there's some epsilon such that if you take any large enough n, there's going to be a string of that length, such that its K capital T complexity and its K little t complexity are very different. So its K capital T complexity is exponential in its K little t complexity. It shouldn't be too hard to see that the K little t complexity is sort of at most a K capital T complexity, right? K little t complexity, you have a program running in time t, and you're just kind of adding log of the time. And with K capital T, you're adding the time. I mean, of course, it's sublinear time bound, but it's somehow more restrictive. And in general, strings with small K little t complexity, strings with small K capital T complexity are going to have small K little t complexity as well. And this shows that the gap between them is exactly the E requiring sub-exponential size problem. So E requires sub-exponential size almost everywhere, if and only exponential size almost everywhere, if and only if this holds for strings. There's a sequence of strings that for which this holds. So gaps between K capital T and K little t correspond to circuit low bounds. And the proof essentially combines this kind of derandomization result of Wigderson with the relationships of non-uniformity and kind of like and kind of membership and exponential time to these two complexity measures. But yeah, I think it's interesting that you're now rephrasing things in terms of these resource-bounded measures. And then he also has a result to characterize next being easy, so next having polynomial size circuits. So just as we had the definition in the previous slide, you can define k capital T sub L of n to be smallest k capital T x over x of length n and L. And then there's these amazing set of equivalences that are proved by Valentin, Russell, and R.V. Wigderson that next present P slash poly if and only if next equals MA, if and only if all next search problems are solved on P slash poly. I mean, this just means that there's a polynomial size circuits which can find sort of witnesses for exponential time verifiable relations, right? So that's what solving a next search problem means. So this was known, and Eric showed that there's also equivalent to something like k capital T sub L of n. The k capital T sub L of n is at most poly log n. If you're familiar with the easy witness method, so essentially this is saying that yeah, like these things happen if and only if like the search problem has an easy witness. A witness is describable by a circuit, and that's what this condition corresponds to. So the polynomial time computable language is essentially a version of the verifier for this next search problem, and then you want the witness for that to be describable by poly log n bits by a circuit, and that's exactly what it means for the k capital T complexity to be small. So yeah, so it's sort of like a new perspective on these results, on the easy witness method and the consequences of that. And in general, what Eric does is that he kind of his characterizations, and there's other kind of observational characterizations he has there, they apply the concepts of Kolmogorov complexity to various sort of important techniques in pseudo-randomness and complexity. So to hardness-based derandomization results. So you can think of all of these as about compression somehow, right? Hardness-based derandomization results show, well, if exp is hard, is non-uniformly hard, then PRGs exist. But if exp is easy, I mean, exp essentially corresponds to like some Boolean function whose truth table is computable in polynomial time the size of the truth table, right? I mean, a language is an exp if and only if its truth table is computable in polynomial time the size of the truth table. And the question is, are such strings compressible or not? And by the k capital T notion. So either they're compressible or else PRGs exist. So you can think of Nissan-Wigderson and Parser-Wigderson as being about compressibility in this sense. The natural proofs result of Rouse-Brown-Rubich essentially says the strong PRGs exist if one-way functions exist. It's hard to distinguish compressible strings from incompressible ones. That's essentially what the natural proofs barrier is saying. And the easy witness method, which I just referred to, and just first in a paper by Valentin and then in IKW, it says that either witnesses to search problems can be compressed, and that makes the search problem easy to solve just by searching over these easy witnesses for a correct one. Or else you can kind of guess the solution to a search problem and use that to de-randomize by applying IW97 and NW94. So this kind of win-win situation. Either you can solve the search problem efficiently by using easy witnesses, or you can de-randomize. You can get some sort of interesting de-randomization. So that is also about compressibility in a different way. And so this kind of like language of resource-bound Kolmogorov complexity can be used to kind of talk about all these different proof techniques and kind of provides a unifying framework for these ideas and techniques. Okay, and then I'd like to say a bit about recent characterization. So this project of characterizing complexity questions that sort of Eric sort of initiated, I mean, that's been quite successful, and especially for cryptography and derandomization, but in other places too. So there's this great result of Liu and Pass, which is very influential in recent connections of Kolmogorov complexity to one-way functions. They show that one-way functions exist if and only if polynomial time-bound Kolmogorov complexity is hard on average of uniform distribution. So that's a characterization too in terms of the hardness of resource-bounded versions. And there's under-characterization based on the hardness on average even of Kolmogorov complexity to approximate. Then it's possible to characterize parallel cryptography by k capital T, as I already said. So one-way functions in NC1, we know that they exist if and only one-way functions in NC0 exist by a famous result of Applebaum, Isha, and Kushlewitz. And this is the case if and only if k capital T is hard on average of the uniform distribution. And then there's under kind of elegant characterization that Liu and Pass have recently. They characterize derandomization. So promise B equals promise P. they have like a meta-complexity condition that characterizes this. Essentially, they say this happens if and only if for every kind of machine M that's trying to solve this certain problem, every probabilistic machine M, and for like Z, like a condition that's long enough, there's going to be an X for which it's hard to distinguish the case where K little t of X given Z is very large from the case where it's very small. So essentially, BPP equals P or promise BP equals promise P is characterized in terms of the hardness of a meta-complexity problem. So that's like a really nice recent result of Liu and Pass. And even more recently, Eric and Shuichi and Harsha, they have this characterization of non-interactive statistical zero knowledge. So for classroom cryptography, purely in terms of meta-complexity, in terms of reductions to the Kolmogorov random strings. And I think this is kind of a project that Eric has been kind of like thinking about for a while about how to characterize complexity classes in terms of the relationship to the Kolmogorov random strings. And this is sort of like surprising and very elegant characterization that they have. So this doesn't quite characterize a complexity question, but it characterizes a class in terms of the relationship to Kolmogorov complexity. And there are several other results. I think even in the upcoming stock conferences, a couple of other characterizations. So this is a very, very active line of work to try to find, to kind of take complexity questions or questions from foundational cryptography and kind of understand how they relate to these fundamental meta-complexity notions. Okay, so now I'm going to move on to the low bound that that Eric shows and what followed on from that. Yeah, you could ask, well, what kinds of properties does this meta-complexity problem MK capital TP have? I mean, yeah, how hard is it? And in his paper, Eric observed that MK capital TP does not have polynomial-sized AC0 circuits, right? So it's sort of hard for AC0. I mean, you'd expect it's very, very hard. You'd expect it's NP hard, but what can we show unconditionally? And he showed this. And the reason why this is interesting is that like standard techniques for showing low bounds, like random restrictions, don't seem to apply so easily to meta-complexity problems. So you can't just like take random restrictions method or the polynomial method and use them in meta-complexity problems. They don't work. You need a different approach. And the approach that often is very effective is an approach based on pseudo-randomness. So what Eric does is he looks at Nissan's generator, which maps polylog n random bits to n pseudo-random bits. And this is known to be secure against AC0. And the crucial observation that Eric made was that this generator can be implemented so that for each seed, Z of set length polylog n, the output is going to have small k capital T complexity. So it's actually clear that it's going to have small k little t complexity, order polylog n. And this is something that Marius Zimand used to show that mk little tp is not an AC0. But then Eric saw that, in fact, these designs in Nissan's generator can be implemented very efficiently. And you have this property. So on the one hand, outputs of the generator have small k capital T complexity. On the other hand, random strings have very large k capital T complexity, close to n. So you can think of k capital T complexity as like a distinguisher between pseudo-random strings and random strings. It can be used to distinguish pseudo-random strings from random strings. But that, of course, means that you can't compute it in AC0, right? Because this is an unconditionally secure generator against AC0. So we can't really compute k capital T in AC0 because we know that k capital T is a good distinguisher. So yeah, so this is sort of like a nice proof, but more importantly, it kind of like it's a paradigm that can be applied elsewhere. What Eric says in this paper is, well, by theorem 15, the theorem that I just said, neither of these classes, so this is just like maybe for now, let's think of it as a different way of saying mk little tp, and this is like mk capital tp. These aren't a non-uniform AC0, and I'm unable to find or construct any other low bounds on the complexity of these problems, other than conditional ones. But then in future work, this was sort of approached, and there's like various sort of kinds of progress on it. So let me just explain what the paradigm is again and kind of abstract it out a bit. So the PRG paradigm is that you have a generator with some non-trivial seed length, S of n, and output length n. You want it to be secure against a class C of circuits, right? So that's what you want. And in some cases, you have that unconditionally, in other cases, not. And let's, to generalize it, say that it has the following property. I mean, you want that the outputs of the generator have small complexity, right? So there's some complexity measure mu. So you want for each seed, for each Z of length S of n, that mu of G of Z is small, is at most S of n, let's say. Then you can in fact prove both unconditional low bounds against weak classes of circuits and conditional low bounds, meaning hardness results, using this paradigm. For unconditional low bounds, you you construct some G that's unconditionally secure against C and having this property, and that would imply that M mu P is not in C. So mu could be K little t, K capital T, circuit size, Ks, space bound complexity, anything you like. And that's just by the same argument I mentioned before. And then you have these conditional low bounds, like if for each F, so the Nissan-Dixon generator is a hardness-based generator, right? So for each function, you have like you can instantiate the generator and get a generator G sub F. And you have the property that if F is hard for C, then the generator is good. And then you can think of this as like a reduction in a way. And so if G sub F is secure against C when F is not in C, and this is a reduction, then it turns out that A is C reducible to M mu P. So essentially you can use this generator-based approach to reduce a complexity class to M mu P in cases where we don't have unconditional low generators, but just hardness-based generators. And both of these sort of like kind of ideas have been used a lot. So there's a very influential paper that Eric, Mihal, and others wrote very soon after he published this paper, where they showed like a slew of hardness results for MK little TP for the space-bounded version. So the easiest to state is that this class is that this language is X-hard under P/poly reductions, just by instantiating the paradigm from before. But in fact, they have much stronger hardness results under NP reductions and under ZPP reductions for the space-bounded version and so on. So they really kind of like use this very effectively. And you can also show that MCSP is hard for polynomial time under NC1 reductions by using the same paradigm. And there's several other results, but here's just a couple of them. And in terms of unconditional low bounds, as I was sort of like saying before, we can now recover almost all sort of explicit low bounds we have. Yeah.
The result in OS17, I remember it's only like average case.
Yes, for average case, yeah. So that's just it. Yeah, and then as I was saying before, almost all explicit low bounds we have, we can recover for these meta complexity problems. So this is shown, it was used to show the MCSP doesn't have subquadratic size formulas, which is not quite optimal because we know almost cubic low bounds and MK capital TP is not H0 mod P. But then, I think Valentin and Renjan and others showed that you have almost optimal results. The MCSP does not have subcubic size formulas, subquadratic size branching programs, or sub-special size AC0 circuits. And this exploits this powerful generator of impulsive Mecca and Zuckerman and kind of applies this paradigm to that generator. So essentially, no low bounds gives you randomness that matches a low bound. And from this randomness, you can extract low bounds from meta complexity problems. So it's kind of indirect. We don't apply the low bound techniques directly, but go through Q randomness, and that works. And then the more recent paper of Shuichi and others shows that MCSP doesn't have non-atomic branching programs of size n to the 1.5. So here again, it's close to what we know in general for explicit problems. Yeah, so there have been various lines of work related to this. And then, so identifies interesting open problems and directions. So let me just maybe quote the paper here. So, I mean, Eric says, Kolmogorov Complexity has been very useful in attacking a wide variety of problems in computer science and mathematics. It has not found much application yet in the field of derandomization. So it is hoped the reductions provided here will be useful in formulating new lines of attack on these problems. And indeed, like the Liu pass characterization that I mentioned, or even the work of Ligia and Roy, which is kind of related to Kolmogorov complexity, does sort of, is implicitly kind of talking about Kolmogorov complexity. And then he says, in particular, it seems quite likely to me that better bounds can improve on the complexity of RK capital T, which we saw before. I'm sure that there are new and interesting implications waiting to be discovered. And since these notions have tight connections to theory of natural proofs, I think it's possible that investigation of these questions will have application not only for study of derandomization, but throughout complexity theory. And hopefully the semester is some sort of evidence of the foresight in this statement. So before concluding, maybe I'd like to say just a bit about Eric, other aspects of Eric, apart from his research. So there's sort of a dozen papers I mentioned here. There's like a dozen more recent papers. I mean, he's clearly done a lot on meta complexity. But he has, of course, all these other facets to him as sort of a colleague, as a mentor, as a friend. We all know how witty and entertaining a speaker he is from his CARP lecture, where he uses his uniquely deep voice and his training in theater to great effect. So we know how great he is as a citizen in the community. I mean, how conscientious he is with his duties, whether it's program committees or editing or reviewing. And I think he's one of the first people we go to for advice if we have kind of questions about some aspect of the community. And he's also a great mentor, not just to people he works with, but to younger researchers in general. I mean, when I was an early graduate student, Eric was one of the most approachable people. And I know he kind of like talks to and cares about the most junior researchers just as much as more senior ones. So yeah, it's great that I mean, Eric is retiring like at the top of his game in a sense, because he has like great recent work and characterizing statistical zero knowledge, an approach to MP versus L. I mean, I wonder if he can resist actually thinking about metacomplexity a bit in his retirement. But even if he doesn't think of metacomplexity will be thinking of him.
So I might have sort of a meta question, I guess. Like, so this says that you can take old questions we would like to understand, like one-way functions, and cast it as something about KT. And that's very nice. But is there a sense in which this gives an approach? Because is KT actually? I mean, if you cannot, if proving that it's not an AC0P took that much effort, is it? I mean, is there any?
Yeah, I mean,
a foothold on the problem for actually attacking its hardness?
Yeah, I mean, it did take some effort, but then it turned out that like all the non-low bounds could be shown also for these complexity problems, right? So I guess it kind of like provides a different perspective. It might be that these characterizations indicate that they're actually barriers to proving these results. So that might be another kind of perspective. I mean, those characterizations help in establishing barriers. But I think, I mean, there's already been kind of quite a bit of progress on understanding these measures and also connecting them to like other notions of complexity. I think sort of like metacomplexity was sort of doing its own thing, sort of very isolated. And I think connecting it to other areas of complexity theory, I mean, to PCPs, for example, and derandomization. So that's, I think there's quite a lot to be done there as well. Because this kind of perspective compression is useful for understanding these areas as well.
I think another answer might be if you look at some of the work that Shuichi Hirahara has done, approaching questions that in the statement of them have nothing to do with metacomplexity, but using these metacomplexity tools to make significant progress.
Yeah, that's now several examples of such results. So worst case average case reductions.
No more questions. Let's thank Rahul again. We'll resume in about 10 minutes.